All right, in the last part of today's lecture, we're going to go through some examples of actual convolutional neural networks that have been used for computer vision tasks and see how some of the components that we learned about are actually used in practice. So the first network that we'll start with is the AlexNet model. The AlexNet model was designed by Alex Krizhevsky and his collaborators and first described in their 2012 paper. This is a fairly well-known model for a couple of reasons. We're going to study it partly because it's a very classic kind of medium-depth convolutional neural network design that is fairly typical of the kinds of medium-depth designs that have been used before. It's a bit like a modernized version of LeNet. But what this particular model is best known for is being the first neural network to attain state-of-the-art results on the ImageNet Large-Scale Visual Recognition Challenge, or ILS-VRC, also commonly known as ImageNet. ILS-VRC is important because it was one of the largest kind of increases in the dataset size over prior datasets, and it was considered at the time in the computer vision community to be a major step up in terms of the realism of the kind of problem it posed for machine learning methods. So AlexNet was well known for being the first deep learning method to really beat so-called shallow learning algorithms on ImageNet, and this was considered a landmark kind of achievement in the computer vision community. So this was in 2012, and you can see that the improvement from AlexNet over the previous winner was enormous, right? So in 2011, it was 25.8% error. AlexNet attained an error of 16.4%, which at the time was considered a huge improvement. All right. Now, what is ImageNet and why was it such a big deal? Well, ImageNet was a big deal for a couple of reasons. First, the ImageNet training set was very large. It consisted of 1.5 million images. As I mentioned in the first lecture of the course, preceding datasets generally had on the order of tens of thousands of images. So 1.5 million training images was a huge step up in size. But also, the ImageNet Visual Recognition Challenge was very difficult. It had 1,000 distinct visual categories, whereas previous benchmark tasks had maybe 100 or so categories. And some of these categories were actually pretty tough. So these are some examples of actual images in ImageNet. So first you have this kind of funny picture showing different kinds of writing implements, and the label for that is ruler. There's a ruler present in the image. There's also lots of other stuff. The words you see below that in red are different guesses that a neural network model might make on this image. Then the second image from the left, that's a king crab or Alaska crab, but it's like zoomed in, it's pretty hard to tell what's going on. Then you have an image that is labeled as sidewinder, that's a type of snake, and you can see the snake is in the image, it actually occupies a small portion of the image. Then you have a salt shaker, but the only way you can really tell it's a salt shaker is by reading that it says salt on it. The model here thinks it's a pill bottle. Then you have a reel, this is referring to a fishing reel, and it's actually a photograph of people standing around, but you can see that one of them is actually holding a fishing reel. So, these are particularly difficult examples, but in general, these are fairly representative of some of the challenges that these models have to deal with when trying to classify the images in ImageNet. So they're meant to be images from the real world. They're actually harvested from Flickr. These are photographs that real people put online and then labeled typically by mechanical Turkers. So this was considered to be a big step up in difficulty and a big step up in realism as compared to previous image recognition benchmarks. So it was a really big deal that a deep convolutional neural network could so substantially outperform the best previous computer vision methods. And in many ways, this result kind of spurred a transformation in the computer vision community away from previously used feature engineering approaches and towards an almost exclusive reliance on convolutional neural networks, which more or less continues to this day. So that's why this result was a really big deal. The actual design of the AlexNet model, however, is actually fairly traditional. So in many ways, it reflects many of the same design decisions seen in LeNet, but scaled up considerably to accommodate this much larger and much more difficult task. So let's talk a little bit about these designs. This diagram is taken from Alex Krizhevsky's 2012 paper, and it looks a little bit strange to us because the network here is drawn as though it were split into two parts. The reason it's drawn that way is because Alex Krizhevsky actually implemented this model to run on 2 GPUs and had to manually split it into 2 parts to run on those 2 GPUs. Now, in 2012, we didn't have tools like TensorFlow and PyTorch, so this was actually implemented manually, and Alex had to actually program it to specify which part of the network would be evaluated on which GPU, and the figure is meant to reflect that. This doesn't actually have any bearing on the functionality of the network. So the 2 GPU implementation, the way it works is it's indistinguishable versus being on 1 GPU, but that's why it was drawn this way. So we don't really worry about this sort of thing these days because now GPUs have enough memory that actually it's not a big deal to keep the whole network on 1 GPU, even for very large networks. In fact, in many ways, the increase in the amount of VRAM on GPUs was partially spurred by the increase in the size of these kinds of networks, because if you wanted to have GPUs in a data center training neural nets, they needed to have enough memory, and you didn't want to do all this manual engineering to split your network across multiple GPUs. Current deep learning packages like TensorFlow and PyTorch will do multi-GPU training for you quite happily, although typically it's preferred to split across batches rather than to actually put parts of the network on different GPUs. But you can do that too. All right, so the input to AlexNet is a 224 by 224 image with 3 color channels. And the first convolutional layer has 11 by 11 filters, and it has 96 of them. And these filters are applied with a stride of 4. Okay, so they are overlapping because they're 11 by 11, but with a stride of 4, so you don't actually put it at every single location. It's fairly common to use strides larger than 1 when your input is so high resolution. So if your input is more than a few hundred pixels, you really want to use larger strides. Otherwise, it'll be computationally very expensive to do this, and you'll end up with your first convolutional response map being extremely large. If we do a little bit of back-of-the-envelope calculation, we can figure out that with this kind of filter, you'll reduce the size of the image by about a factor of 4, minus the edge effects due to the padding on the sides. So that actually gives us an activation map that is 55 by 55 with a depth of 96. And that is conv1. That's the first convolutional layer in AlexNet. After this convolution, just like always, we apply a ReLU activation. Generally, for all the networks I'll describe today, if there's a convolution or fully connected layer, it's followed by a ReLU activation. These are very commonly used for deeper networks for reasons that I'll discuss actually at the end of this part. So I'll typically omit the ReLU part, but keep in mind that it's always there. Every time you see conv or fc, there's always a ReLU after it, except for the very last fully connected layer, because that goes into a softmax instead. Okay, so the first conv layer produces 55 by 55 with the depth of 96. And you can see in the diagram at the top, it shows the first conv layer being 55 by 55, but it's actually labeled as 48 because it's split into 2 parts. So there's 2 parts that are 48 each, and you can imagine stacking them and you get 96. Then there's a max pooling layer, and this max pooling layer is 3 by 3, but it actually has a stride of 2. So before we talked about how pooling layers typically are non-overlapping, but they could be overlapping, and here it happens to be an overlapping pooling layer. So it pools everything in a 3 by 3 region, and then slides this 3 by 3 window with a stride of 2, so there's a little bit of overlap between every pooling. Typically, the size of the pool and the stride are equal, but here they're not. So because the stride is 2, this actually downsamples the image by a factor of 2, except for the edge effects. So because of the 3 by 3 size, there's actually a little bit of padding on the side, so that's why you get down to 27 by 27, right? 55 doesn't divide by 2, but you lose 1 pixel due to the padding. So then you end up with 27 by 27, and the depth is preserved because pooling is done independently on every feature. Then you have the next layer of convolution. So here, pooling without overlapping regions, and then you have the next layer of convolution. Now, as a pop quiz, how many parameters are in the first convolutional layer of AlexNet? Okay, so to determine the number of parameters, we know that we only have to look at the filter size, right? Because the number of parameters is independent of the input and output size, it depends only on the filter. And the filter is 11 by 11 by 96. Now remember, the size of the weight matrices in each of those convolutional layers is filter height by filter width by input dimensions by output dimensions. So 96 is the output dimension. The input dimension is 3 because the image has 3 color channels. So you end up with 11 by 11 by 3 by 96 for the weight matrix. So the number of entries in that weight matrix for conv1 is 11 times 11 times 3 times 96, which is 34,848. Now, are we missing something? Are these all the parameters that are present in conv1? Take a moment to think about this. What other parameters do we need to have? Well, if you think back to those linear layers, if you remember we talked about how for linear layers we have the weight matrix, but we also have a bias vector. And we have that for convolutions too. Now the number of parameters in the bias vector doesn't depend on the number of inputs, it just depends on the number of outputs. And the number of outputs is always 96. So there are 96 parameters in the bias, which means that for every time we evaluate that filter, we pass it over every point in that 11 by 11 region, do our 96 by 3 matrix multiply, sum all of those together, and then for every one of the resulting 96 entries, we add the corresponding dimension of the bias. So that adds 96 more numbers. That's a fairly small number, and that results in the total number of parameters being 34,944, which is quite a few parameters. It's still much, much lower than what we would need if we had a fully connected layer, if we had a standard linear layer going straight from the image to a fully connected activation layer. Okay, now I'm not going to draw the rest of AlexNet piece by piece because that would take me forever, so I'm going to write it out instead. So the first conv layer, as I mentioned before, 11 by 11 by 96 filters with a stride of 4, and they map 224 by 224 by 3 images into 55 by 55 by 96 activations. And they actually do this without zero padding. So that's why the reduction in size is actually a bit larger than just dividing 224 by 4. Then you have pooling, again without zero padding, and that gets us down from 55 by 55 by 96 to 27 by 27 by 96. Then AlexNet actually has something called a local normalization layer. This is not widely used anymore, but it's meant to take the activations in each patch and put them on roughly the same scale so that there aren't big low frequency differences. And this is useful for images because if there are changes in lighting like shadows, this tends to kind of make that a little less pronounced. This is not really widely used anymore. There are other kinds of normalizations that are used that we'll actually discuss in the next lecture, so don't worry about these norm layers. Then there's another convolutional layer, and this one has 5 by 5 by 256 filters. So the filters are deeper, they're more filters, but they're smaller. Why are they smaller? Well, because the first conv is operating on a 224 by 224 image, so it makes sense you want to have larger filters because you have a high resolution image. The second conv layer is operating on a 27 by 27 activation map, so you don't need such large filters to incorporate a large spatial region. There are more filters because you want to basically pull out more complex, more abstract information, which intuitively means that you have more numbers that are needed to describe what's going on at each location, right? So this is not really what the network is doing, but a kind of one story you could imagine here is that every location in the original image just has 3 colors. Every location in the first activation map maybe describes what kind of edge is present at that location. After conv2, maybe it describes what kind of part is present at that location. And there are many more different parts than there are different edges, and there are many more different edges than just the 3 color channels. So it makes sense that you would want more filters, more features, and lower resolution as you go up in the network. So you want more features because there are more different things that could be going on, and you want lower resolution because eventually you want to get down to just one label. All right, so after conv2, we have another pooling layer. And just like before, it's 3 by 3 with a stride of 2. Okay, kind of something that I guess Alex Krzeszowski liked to do. So 3 by 3 by 256, stride of 2, takes these 27 by 27 by 256 maps into 13 by 13 by 256. And again, the reason it's not exactly a factor of 2 is because of the additional padding on the edge, because it's 3 by 3 instead of a 2 by 2. Then you have another local normalization, And then there's another conv layer. And this one is 3 by 3 by 384. So you're probably seeing a pattern. The size of the filters goes down, the depth goes up. So that takes our 13 by 13 by 256 into a 13 by 13 by 384. And this time we are using zero padding. Why are we suddenly using zero padding for conv, whereas we weren't on the first layer? Well, because the first layer had such a high resolution image that losing a few pixels off the sides was not a big deal. By the time we get to 13 by 13, if we didn't do the zero padding, we would lose a lot on the sides and potentially actually miss out on some useful information. Then we have another conv layer. At this point, we don't need to stick another pooling layer in there because we're already down to 13 by 13, so reducing that any further would be maybe a little counterproductive. So we'll just stick another conv with stride 1 on that, and so the size will be preserved. So we take our 13 by 13 by 384, and we take it to another 13 by 13 by 384. So we're just doing some processing at this point. We're not trying to downsample further. Then there is a slightly smaller convolutional layer, 3 by 3 by 256. So that takes our 13 by 13 by 384 into a 13 by 13 by 256. There's a small typo here. It says 13 by 13 by 256 to 256. It should be 384 to 256. Then there is our last pooling layer. And at this point, we're just trying to pool things down so that we can turn it into a single number. So we're going to take our 13 by 13 by 256, and we'll do a regular stride 2 pooling, although here, again, it's a 3 by 3 pool with a stride 2, so we still cut off that last pixel, and we get a 6 by 6 by 256. At this point, things are small enough that we can simply flatten them into a big vector. So there we get the first fully connected layer. And that first fully connected layer takes our 6 by 6 by 256 and it flattens it into a giant vector. So that means that basically we stack up those 256 length feature vectors one on top of each other for every one of those 6 by 6 positions. So we get 36 of these 256 length vectors that are all stacked up, and the total length of that is 9,216. And the first fully connected linear layer takes this to 4,096, followed by a ReLU, of course. So that means that the size of this matrix is 4,096 by now 9,216. So it's actually a very large matrix. It has millions of parameters in it. In fact, it is the largest layer in terms of the number of parameters. Then we have another fully connected layer that takes 4,096 to 4,096. And then the last one takes 4,096 to 1,000 because we have 1,000 possible classes. And after this, there is no ReLU anymore. There's just a softmax, which outputs the answer. So this is the architecture for AlexNet, and it's a little bit ad hoc. So there was some experimentation that went on into designing this, but you can see a few patterns. You can see that pooling layers reduce the size of the activations in terms of their spatial extents. We can see that the number of features tends to go up as you go deeper. So we're trying to summarize all the information in the image with lower resolution activation maps that are deeper, which helps us represent more abstract features. And once things get small enough, then we flatten them and put them through a few fully connected layers to produce an answer. Now, don't forget, we have ReLU nonlinearities after every convolutional RFC layer except for the last one. And this network in Alex Reshevsky's paper was trained with a number of regularization techniques that were meant to make it work a bit better, including data augmentation. We'll talk about that later, but that basically involves taking your image and transforming them in various ways, like changing the hues and saturations and brightnesses to basically teach your network about some invariances, as well as a regularization technique called dropout, which we'll discuss later as well. As well as these local normalization layers, which are not used very much anymore, but we'll talk about other kinds of normalizations that are used in the next lecture. Okay, so this is AlexNet, and this network is, in some ways fairly classical. It's fairly representative of kind of medium depth networks with large fully connected layers at the end, and these are, a fairly popular class of networks. However, the best networks these days for processing visual inputs tend to be quite a bit deeper. So next we're going to talk about the VGG network. To use an overly poetic metaphor, if AlexNet was a work of art, VGG was a work of engineering. Essentially, the patterns that we'll start seeing in the VGG network will be a degree of standardization and modularization, which will really help us when we have to build very, very deep networks. Because with AlexNet, it's pretty clear that the Parameters of every layer were carefully chosen by hand. With VGG, we'll start seeing kind of common motifs repeated multiple times as a way to increase the depth of your model. So why is the VGG network important? It's still often used today, so typically people don't use AlexNet much these days, but VGG is sometimes used. VGG has a big increase in depth over the previous best model. So VGG on ILS-VRC was first reported in 2014, 2 years after AlexNet, and it had more than a twofold increase in the number of layers over the previous winner. So here's VGG. And we start seeing these kind of homogeneous stacks of multiple convolutions interspersed with resolution reduction, fairly standard motifs that will come up again and again as we further increase the depth of these models. Okay, so let's go through the architecture of VGG. The diagram here on the right actually shows it pretty nicely, and you can see how these feature layers are getting deeper and smaller, but let's actually walk through what they look like. So the first thing we do with VGG is we take our 224 by 224 by 3 image and we hit it with stride 1 zero padded convolutions. So there is no resolution reduction. These are gigantic activation maps. But the filters are actually very small. The filters are only 3 by 3 by 64. So we have these small little filters, and they're applied to these gigantic images and activation maps. So that means we take 224 by 224 by 3 to 224 by 224 by 64, and then we do that again. And then we reduce resolution. We don't want to stay at 224 by 224 for too long, because this is using enormous amounts of computation and enormous amounts of memory to compute the filter at all those locations. The number of parameters here is actually very small. In fact, these layers have some of the smallest number of parameters. But the activation maps require the largest amount of memory. So we'll downsample it by a factor of 2. So this is a standard 2 by 2 non-overlapping pool. So very straightforward, just takes our 224 by 224 into 112 by 112. Then we're going to hit this with 2 layers of identical convolutions. These are 3 by 3 by 128. So just like before, we're increasing the depth as we proceed. So we reduce resolution, increase depth, just like before. But now it's sort of very, very convenient, just increase it by a factor of 2, from 64 up to 128. So we end up with a 112 by 112 by 128. The picture, of course, is not to scale. The depth is actually larger than the width at this point. And then we pool it again. Standard 2 by 2 pool gets it down to 56 by 56 by 128. Then we have 3 layers of identical convolutions. Again, stride 1, 0 padding, 56 by 56 by 256. Okay, so resolution halved, depth doubled. And you're probably starting to see the theme here. We have another 2 by 2 pool, half the resolution, 28 by 28 by 256. And then we have a deeper convolution, 3 by 3 by 512. Okay, resolution is halved, depth is doubled. And then we do this 3 times again. Then we pool again. Now at this point we have filters of depth 512. Maybe we don't need much more than that, so we'll stay at 512 and do this again. Okay, so now you can see the motifs here. We have 2 to 3 layers of convolutions that don't reduce the resolution at all, interspersed with pooling layers that reduce the resolution by half, and each time we reduce the resolution by half, we typically increase the number of filters. Then we pool one more time to get it down to 7 by 7 by 512, and at this point it's small enough that we could construct our first fully connected layer. Now, when we stack up all of those 512 feature vectors for every one of the 7 by 7 positions, we actually end up with a very long vector. It's over 25,000 entries. So that first fully connected layer is actually quite enormous. It has over 100 million parameters. Then we have our regular 4,000 by 4,000 fully connected layer, then one more going into 1,000 categories, and then our softmax, just like before. Okay, so what are we seeing with this network? Well, we see multiple layers between each pooling operation. So in some ways, you can think of this as a slightly neater version of AlexNet with just multiple cons between each pool instead of just one. More layers means more processing. So that's why we see these repeated blocks. We're just cramming in more processing in between the resolution reductions. Which parts of this network use the most memory? Well, the most memory is actually used at the beginning, because at the beginning we have these gigantic activation maps. So even though the filters are small, the amount of memory needed to store those 224 by 224 by 64 activation maps is very large. So most of the memory usage and also most of the computation ends up taking place in the earlier layers. Which parts have the most parameters? Well, the number of parameters actually is largest in the fully connected layers, where we flatten the activations into a giant vector. This will come up again later. So almost all the parameters in VGG are actually present in that first fully connected layer. The rest, in terms of the number of parameters, are actually much smaller. In the convolutional layers, the parameters kind of peak around the 28 by 28 by 512 layers, right? So those are the 3 by 3 by 512 filters. This is not actually a good thing, and we'll see later that in more recent architectures, people have actually gotten rid of this. You actually don't want most of your parameters living in that first fully connected layer. But other than this, kind of the notable thing about this design is that you have these motifs and you repeat them multiple times to increase depth. All right, so the last network we'll talk about is Resnet. And Resnet is a very popular architecture that is very widely in use today. And when it was first introduced, it was introduced with 152 layers. Since then, people have used similar ideas to scale up networks to thousands of layers. But Resnet 152 is actually still pretty good. So it's not actually clear how much more you need, although you can, if you want to squeeze the most performance out of ILS-VRC, you could go bigger. All right, so there's Resnet. This is 2015, 152 layers. Error rate of 3.57%, which is actually better than human-level performance, at least according to Andrei Karpathy. This is a visualization of Resnet in comparison to AlexNet and VGG from Kai-Ming He, who was the first author on the Resnet paper. Now, of course, he had to shrink everything down to fit all the layers, so you can hardly tell what's going on. You can just see that AlexNet is this little block on the left, VGG is a slightly larger block in the middle, and Resnet is this giant monster on the far right. So to understand how Resnet works, it probably helps to look at slightly scaled down diagrams. Resnet uses a very familiar pattern. The pattern is not entirely unlike VGG. So it's a collection of these 3 by 3 convolutions with filter sizes that go up by factors of 2 each time you pool, but there are many, many more of them in between each pooling operation. So since we can't draw the full Resnet model and have it fit on this slide, what I'm going to show you instead is a diagram of a heavily simplified 18-layer prototype. The full 152-layer version is basically analogous to this, except that everything is kind of stretched out. Quite a lot, actually. So we start off with one 7 by 7 conv, which is the only 7 by 7 conv, and that's just because the initial resolution is pretty large. So that gets us down to a slightly lower resolution thing. And then we have these repeated blocks of 3 by 3 convolutions with resolution reduction in between them, and the number of filters goes up by a factor of 2 as we go until you hit 512, and then you stay at that. The actual convolution operations here are a little bit different than the standard ones in VGG, and we'll talk about that later. So that's what the little skip connection label is showing us. But don't worry about that for now. The other notable feature of this model, and this is something that cropped up in other kind of models at the time, is instead of having this giant fully connected layer at the end, we simply take our last convolutional response map and we average pool it, which means that we average the feature vectors at every location. So we don't stack them, we just average them all together. So that means that we have 512 filters at the end. We'll be left with a vector of size 512, not 28,000 or something. And then we just have one linear layer going right into the softmax. So we take that 512 directly into 1000 labels. So we basically cut out that entire fully connected block at the end. This might seem peculiar because those fully connected blocks were really, really large in terms of the number of parameters before. But it turns out that these models actually end up doing most of their visual processing in the convolutional layers, and you could actually just get rid of the fully connected parts at the end and just do average pooling and just one matrix going straight into the 1,000 classes, and that actually ends up working pretty well. So by doing this, we've eliminated a very large chunk of the number of parameters, leaving us with more processing and parameters to play with for the convolutional layers, which are the ones that are going to be doing all the heavy lifting. All right, so let's talk about why the Resnet can actually train with such a large number of layers. So these are some experiments that were conducted by the authors of the Resnet paper, studying the effect as we increase the number of layers. This is a simpler data set. This is CFAR10. It's a much smaller data set than ImageNet with many fewer classes. And on the left, you can see their experiments with a standard convolutional network as you increase the number of layers from 20 to 32 to 44 to 56. And what you can see here is that the error rate actually increases as the number of layers increases. Now this is for very deep networks. Remember, AlexNet and VGG were both smaller than 20 layers. So if you go to like 10 or 5 or 3, then you'll see the opposite trend. So essentially what happens is that as you increase the number of layers for a conventional convolutional network, accuracy improves, so error drops, but then after a while it goes back up again. So it decreases, decreases, decreases until you get to about the depth of VGG, and then as you go above 20, it starts increasing again. What the Resnet people figured out is that with a small modification to the neural net architecture, you could actually reverse this trend. You could actually get it so that for 20 layers, their accuracy is about the same, but with their design, as the number of layers increases, accuracy continues to improve. Now on CFAR10, it appears to saturate at around 100, but CFAR10 is an easier data set than ImageNet, so for ImageNet, you continue to see increases as you make it bigger. All right, so what's the main idea? What is it that actually allowed the Resnet folks to be able to train these larger, much deeper networks? Well, the idea is something that has come to be called the residual layer. The change from a regular layer to a residual layer is shown in this diagram borrowed from Cunningham. So here you can see that in the regular network, you have your weight layers, which can be convolutions or fully connected, doesn't really matter. So whatever they are, let's say they're convolutions, and you just apply them in series. For a residual network, you take every group of 2 convolutions, and you take the input to the first one, let's call that x, and you add that to the output of the second one. So if the regular network, if you can consider every group of 2 convolutions computing some function h of x, in the residual network, that group of 2 convolutions will be computing h of x equals f of x, which is just the 2 layers together, plus x. So you get this kind of skip connection. X gets to bypass those convolutions that get added at the end. You can almost think of it as each pair of layers is computing a modification to the activations instead of entirely new activations. So it's taking the old x and adding f of x to it. Now, why do we skip over just 2 layers? It's a fairly arbitrary choice. It doesn't have to be 2, but that's a convenient choice to make. All right, so the intuition is that you compute a change to x instead of just an entirely new x. Why is this a good idea? Why does this actually make it possible to train much deeper networks? Well, it turns out that there's actually a pretty good mathematical reason for this. And to understand that mathematical reason, we first need to understand a little bit why it's so difficult to train very deep networks. Let's think back to our example when we tried to apply chain rule for our small little 2-layer network. So chain rule just looks like a multiplication of a bunch of Jacobians. So in general, for some arbitrarily deep network, you could imagine that the derivative of the loss with respect to the weight matrix of the first layer will be a product of a huge number of these Jacobian matrices, and then at the end you multiply it by dl dzm, right? So these Jacobian matrices, they can be all sorts of different things, derivatives of nonlinearities, derivatives of linear layers, derivatives of convolutions, but there's just a whole bunch of them and they're all matrices and you multiply all of them together. So if we multiply many, many numbers together, what will we get? Let's forget that they're matrices for a minute. Let's imagine they're just numbers, they're just scalar values. If we multiply a huge number of scalar values together, what will be the answer? Well, you might say, I don't know, you haven't told me what the numbers are. But actually, if there are enough of them, In most cases, there are only two possible answers. Strange but true. If you multiply many, many scalar values together, if there's a huge number of them, usually you will get one of two answers. What are these two answers? Well, if most of the numbers are less than 1, you're going to get 0. Because if most of the numbers are less than 1, then your answer looks something like a number less than 1 raised to a very, very large exponent. Whenever you multiply two numbers that are both less than 1, you get something that's lower than either of the two numbers. So if you multiply lots and lots and lots of these together, eventually you get very close to 0. If most of the numbers are larger than 1, then you get infinity. Because if you multiply two numbers together that are both larger than 1, the result is larger than both of those numbers. So if you multiply many, many numbers that are larger than 1 together, you get infinity. So strange but true, if you multiply many, many numbers together, there are really only two possible answers, in most cases. There's a very small set of cases wherein the answer is more interesting. And that small set of cases is when all the numbers are close to 1. So that means that the only time that you get a reasonable answer from multiplying together many, many, many Jacobians is if they're all pretty close to 1, because otherwise things will go to 0 or infinity. And the same logic actually applies for matrices. So this is, by the way, why we like using rectified linear units instead of sigmoids, because the derivative of a rectified linear unit is the indicator of whether the input is positive, which is either 0 or 1, which means that a large fraction of those derivatives are just 1. Some of them are also 0, but the rest are all 1. So for matrices, being close to 1 doesn't mean that every entry is 1. It actually means that the matrix is close to identity. More generally, if you're pretty well versed in linear algebra, there's actually a more general condition. It's actually the eigenvalues of the matrix need to be close to 1. But if it's identity, that's good enough. So it's sufficient but not necessary. Okay, so we would like our Jacobians to look like identity matrices if we can help it, because that will prevent their product going to 0 or infinity. In the regular conv layers, our derivative dh dx could be big or small. It doesn't have to be close to 1, which means that if you have a huge number of conv layers, when you multiply their Jacobians together, the resulting derivative could go to 0 or infinity. Oftentimes it actually ends up going to 0. If, however, you have this residual layer, dh dx is df dx plus identity, because you're just adding x. So as long as the weights in the conv layers are not too big, you might hope that this df dx would not be too big either. So this first term would be pretty small, and you would have some small thing plus identity, which would be pretty close to identity. In fact, as long as df dx is kind of centered around 0, you'll basically end up with identity plus a small number or identity minus a small number, and those deviations would hopefully not go too far one way or the other, which would allow you to multiply lots and lots of these Jacobians together. So that's basically the rough idea for why resnets work. So the ingredients of the resnet, we have these generic blocks with many layers interspersed with a few pooling operations. So we take kind of similar to what we have in VGG, we have these 3 by 3 by something, and we apply them many, many times. But they're all residual blocks. There's no gigantic fully connected layer at the end, just mean pooling over all xy positions, and a smallish fully connected layer to go into the softmax. Less than 1 million parameters at the end. The residual layers provide for good gradient flow, and that's what makes this network work really well. And this basic design is actually very popular these days for visual processing, and it's a really good way to build really deep networks with very good gradient flow.